Okay, let's have a second go at narrating this one then as my first time the sounding record. It says fundamental particles summary, but actually I am going to do a little bit of new work. We're just going to have a look at what the consequences of quarks were. The last video that I did was quarks, and so we need to just look at the consequences of that, and then I'll round everything up. And you'll actually be surprised how little there is to the particles course now that you've understood it in the final summary that I'm going to go through. The classification, this is the classification that we ended with on the previous video, so should make sense to you. And so in terms of particles, we now have leptons. And leptons are fundamental particles which do not take part in the strong interaction. Okay, on the mark scheme, that's what they're going to want you to say. Do not take part in the strong interaction. They don't want you to say electron family or anything like that. Fundamental particles which do not take part in the strong interaction. And then we have the hadrons, and they are particles which do take part in the strong interaction. Okay, and so that's the fundamental difference between these two. The temptation with hadrons is to say made of quarks, because of course they are. But made of quarks is not always on the mark scheme. Sometimes it is, sometimes it isn't. So you are much better off to say strong interaction. Much better off to say strong interaction. And then hadrons fall into two categories. We have baryons and we have mesons. And baryons are conserved and mesons are not conserved. So you remember that the proton cannot decay away because the proton is the lightest of the baryons, and so there is nothing more that a proton can decay into and conserve baryon number. So the proton lasts, proton is stuck. The mesons, on the other hand, where they're made of a quark and an antiquark, and each quark has a third of a baryon number, we get 1/3 of a baryon number on the quark, and then we get minus a third of a baryon number on the antiquark, and the end result is that there is no baryon number associated with mesons. There is no special conservation rule associated with mesons. And then we have the exchange bosons, and you don't really have to know a whole lot more about those than what they are. So that's EM, that's weak, and that's strong. You're also expected to know that pions are the exchange particles for the strong nuclear. So the pions stick the protons and the neutrons together. It's the strong force that's doing it, really, but the strong force requires gluons and quarks, and gluons and quarks don't exist on their own. They've got to be packaged up. And so the strong force does the exchange between the protons and the neutrons, packaged up as pions, because of the rules that don't allow them to exist separate. And so the pions do the exchange on the behalf of the strong force, and we refer to the resulting force as the strong nuclear. Now, beyond that, the contents of that first page, the main thing that you have to learn are the contents of this page. Energy is conserved. Now, it's energy and mass really that's conserved, because you know by now that mass can be converted into energy. But on our course, we refer to mass as rest energy anyway, so it's energy and energy is conserved. Momentum is conserved, and sometimes that's on mark schemes. You can write that down and you get a mark. Charge is conserved. So this is the first of our important new conservation rules that all of the interactions that we've been discussing depend upon. So charge is conserved. That electron has to be manufactured during beta decay in order to conserve charge. Otherwise, the neutron can't turn into a proton and rearrange the nucleus into a more stable state. Lepton number is conserved. That's why we have all these antineutrinos, to conserve lepton number. And if more than one lepton flavor is involved, lepton flavor is also conserved. So that one, the only place you'll likely come across that is muon decay. When a muon decays, two neutrinos are formed, an electron neutrino and a muon neutrino, in order to conserve both muon flavor and electron flavor. So we've got the lepton number, the overall thing being conserved. We've also got the three individual lepton flavors being conserved. Usually it's just lepton number that turns up in your exam, but there's no reason why lepton flavor couldn't turn up in your exam, and it certainly has on previous specifications. Baryon number is conserved, just discussed that one. Strangeness is conserved under the strong interaction. Now, this is the weird one. You remember Murray Gell-Mann. Strangeness is conserved under the strong interaction, and strange particles are made under the strong interaction. So strange particles are always made in pairs. There's always a strange quark and an anti-strange quark, so that strangeness remains conserved under the strong interaction. The trouble with that is that would mean that if, in order to decay away via the strong interaction, the strange particles would have to wait around until there's another strange particle. Because you'd need both of them in order to be able to conserve strangeness when it decayed away. So strangeness doesn't decay away under the strong, strangeness decays away under the weak, where strangeness is not conserved. Peculiar, just got to learn it. Right, let's have a look at the consequences of quarks for the weak interaction. Now we can do all the things like charge conservation and baryon conservation. If I do baryon, that's a baryon. That's a baryon. That's not a baryon. That's not a baryon. Yes, baryon number is conserved. So we can do all of those things. Hopefully you remember how to do all of those things. But we can also think about the quark composition. So a neutron is an up and two downs. And that's going to a proton, which is two ups and a down, plus our consequences of the decay of the weak W boson. So if you have a look at this, you can see that clearly what must be happening is that one of the downs is turning into an up. And so we can discuss the weak interaction as one single quark changing type. So that's what's going on under a weak interaction. One quark is changing type, emitting a W boson. The W boson will then decay into something else. So I can draw that. Well, I think actually I've got it drawn. Yes, there you go, I've got it drawn. And so what we have here is we have a down turning into an up, and the other up and down not changing. Now we need to check things, conservation rules. So for example, charge conservation, well, down is minus 1/3, isn't it? And an up is plus 2/3. So plus 2/3 minus our whole charge lost for the W, that leaves us minus 1/3, which is what we started with. Yes, that's correct. And then just W we know is making a negative charge and a neutral charge, and so charge conservation is happening there, and charge conservation is happening there, even if we only consider it in terms of the single quark, and we don't worry about what the other two quarks are doing. And so we can write beta decay as down turning into an up, plus the electron and the empty electron neutrino. This is another weak interaction, and so this is electron capture. And so if we consider electron capture, then let's do lepton number conservation. Proton's not a lepton, electron's a real electron, a neutron's not a lepton, and the electron neutrino is a real lepton. Lepton number is conserved. And if we write it in terms of quarks, we've got two ups and a down, plus our electron, going to an up and two downs, plus our anti-electron, but it's our real electron neutrino. So there's our in quarks, there's it in quarks. We've got one of the ups turning into a down, one of the ups turning into a down, and that's going from plus 2/3 charge to minus 1/3 charge, and we're getting plus 1 coming out here. Plus 1 plus minus 1/3 gives you plus 2/3. That's correct. So we do indeed have charge conservation, and I guess we'll check it here. We've got plus 1 meeting minus 1, ending up with neutral. Yeah, that's correct. So we get charge conservation at both those vertices. And so electron capture can be written as an up turning into a down, with the capture of an electron and the emission of an electron neutrino. So you have to look for this when you're doing your exam questions, because sometimes they say mark on the particles on the particle interaction diagram. Sometimes they say mark on the quarks. Sometimes they say write it in terms of particles. Sometimes they say write it in terms of quarks. So if you were asked to do the electron capture in terms of quarks, this would be your equation and this would be your diagram. Although you wouldn't lose marks if you didn't put the extra 2 on the side here that aren't actually doing anything. So if you left out those 2, you wouldn't lose marks because they just make the drawing complicated. But when it's drawn properly, those 2 are drawn in. Right, strangeness decaying away. Now this is something close to what an exam question might be. The omega minus baryon decays to a xi naught and a pi minus via the weak interaction as shown below. Given that the strangeness of the omega is -3, deduce the strangeness and the quark composition of the xi. Now, you'll remember that you don't have to learn anything about the hyperons. And so you're looking at that going, but he told us we didn't have to learn anything about the omega or the xi. And it's quite right, you don't have to learn anything about the omega and the xi. You can work it all out from the information given in the question. So let's have a think about the information given in the question. First thing is, you did have to know something about the pi. So a pi minus, well, the only way to make a pi is not strange, so it's ups and downs. The only way to make it negative would be to have a down, which is -1/3, and an anti-up, which is -2/3. That would give me a charge of -1. So there's the quark composition of pi. Now my omega. The omega is -3. Now if you look at your table of quarks, a real strange quark has a strangeness of -1. So the only way the omega could be -3, and we're told it's a baryon, so we know it contains 3 quarks. The only way the omega would be -3 is if it contains 3 s's. You probably knew that. You probably remembered that from our previous discussion of the omega, but you don't have to know that because they told you it's -3. And the only way you can build an omega is from 3 strange quarks. Right then, now what else do we know? Well, of course, we know that under the weak interaction, strangeness disappears 1 step at a time. And now, of course, you realise that what that means is that the weak interaction is changing one of the strange quarks into something else, because that's what this weak interaction does. It changes the type of quark. So 2 of these stranges won't change because it's the weak interaction. It only changes things 1 at a time. And so we need the third one. What's the third one turned into? Now, it's got to add up to 0. And again, you go to your table, and your table tells you that a strange quark has a charge of -3. So I've got 2 lots of, sorry, -1/3. I've got 2 lots of -1/3, and that means in order to make it balance out at 0, I need a +2/3. And of course, a non-strange +2/3 is a U. So there you go. There's the quark composition of our xi. So quark composition is SSU, and the strangeness is -2. Okay. Now we can even go further than that. We can draw the Feynman diagram, the particle interaction diagram, because we know we've got 2 S's that don't do anything. And then we've got 1 S that's turning into a U. Now, that's then got to emit a W. What W is it going to emit? Well, this is a charge of -1/3. And this is a charge of +2/3. So what have I got to add to +2/3 to make -1/3? I've got to add -1, haven't I? So W negative. And then what's our W decaying into? Well, our W is decaying into this pair of quarks here. Our W is decaying into down and anti-up, which of course have a charge that add up to -1. So charge is conserved there, and charge is conserved there. Charge is conserved, strangeness is not conserved, it's disappeared 1 step at a time. That's almost certainly the correct Feynman diagram, and particle interaction diagram that we've drawn there. Hurrah, get a mark. Now the thing is, you never will get a mark because they won't ask you to do anything that complicated. They'll ask for this bit, they won't ask for this bit. But it's interesting to see that you can, because you understand the rules. Have a look at another one. So lambda 0 going to a proton and another pi minus. The lambda naught is a strange particle which decays to a proton and a pi minus via the weak interaction, as shown below. Show that the lambda must be a baryon and deduce its quark composition. Well, how do we show the lambda must be a baryon? Well, we know the proton's a baryon. So if we do conservation of baryon number, we've got +1 for the proton. We know that the pion is not a baryon. And the only way that works is if the lambda is a baryon. So there you go. The only way that works is if the lambda is a baryon because of the baryon conservation rule. Deduce its quark composition. Well, of course, the proton is 2 ups and a down. The pi we've just done on the question before. To make it add up to -1, we need a down and an anti-up. What's our lambda? Well, we know that it must be singly strange. We know it's going to have one strange quark, because if it had more than one strange quark, there would be a strange quark left over here, and there isn't a strange quark left over there. So it must have one strange quark, so we know that much. It's got to have a strange quark. And that strange quark is turned into either an up or a down. And we've got to make it have a total charge of 0. Well, how can we make it have a total charge of 0? If that's -1/3, the only way we can make it have a total charge of 0 is if that's a D, which gives us another -1/3, and that's an up. Effectively, the lambda is a strange neutron. Okay, and again, you wouldn't be expected to do this in the exam, but let's have a look. What have we got? We've got a U not changing. We've got a D not changing, and then we've got an S, and that S is becoming a U. And we know from the previous one that means it's fired out at W minus, and that W minus, just like the previous one, has decayed into a D and an anti-U. There you go. Bish, bash, bosh. And we can work all of that out. We don't have to know anything much in advance, apart from the quark compositions of these two. We don't have to know anything else in advance. They'll tell you it in the question. We know it's a baryon. We know it's got to have 3 quarks. We know it's strange. We know one of them's got to have strangeness. Can't be more than one because there would be some strangeness left on the other side because only one step at a time disappears over the week. Right, let's keep going. Decaying of strangeness. Write out the composition of each. Well, we've just done the pi minus, haven't we? So we know that's a down and an anti-up. Now the pi plus is the antiparticle pair of the pi minus. So that's going to be an up and an anti-down. Just check. Plus 2/3, opposite of -1/3, another third. Yeah, adds up to +1. Right, and then it says that the kaon has a strangeness of +1. Now you ought to remember this, but it tells you in the question, so there's no need for you to remember that. So it's got a strangeness of +1. Then we know it's not got a strange quark in it, because a strange quark is a strangeness of -1. It's got to have an anti-strange quark. Now, what's it going to pair with an anti-strange quark in order to give us 0? Well, the anti-strange quark is going to have a charge of +1/3, so we need something with a charge of -1/3. It's going to be a D. Okay. So let's have a look what happens here. So we've got a D that's unchanging. We've then got a strange S. Now, a strange S can't turn into a D because that would be a charge change of 2/3. That's not allowed. So it can go into an up though. So it must be that. It must be this. Must be what's being made. It must be going into an anti-up because that's +1/3. Ending up at -2/3. So what have I got to add? That's a -2/3 to make +1/3. The W that's fired out this time must be a W plus. And then the W plus is going to decay to give us that positive pion. So it's going to decay to give us an up and an anti-down. All right. As I say, you don't have to draw the diagrams. I don't think they're ever going to ask you to draw a diagram from anything this difficult. They're most likely to ask you to do that. And there could easily be 6 marks for that. Right, then finally in these examples, let's have a look at strangeness being created. So the following is the result of a strong interaction. So strong interaction tells us that we're creating strangeness, and it also tells us that strangeness is conserved. Important. Show that the omega minus must be a baryon, and by deducing the quark composition of the particles, show that it has a strangeness of -3. Now you of course know this because we've just done an omega minus. We've done omega minuses previously, of course. You know it's a baryon. You know it's made of 3 strange quarks. But for the purposes of the question, you don't know those things. So let's have a look at what must be going on. Right, first thing, show it must be a baryon. How do we show it must be a baryon? Well, we do conservation of baryon number. Kaon's not a baryon. Proton, real baryon. Kaon, not a baryon. Kaon, not a baryon. So the only way this all matches out in terms of baryon number is if the omega is a real baryon. So easy. Yes, omega is definitely a real baryon because of conservation of baryon number. Right, let's have a look at the quark compositions. Well, we've just done the K0, so we know that the K0 is an anti-S and a D. I've said to you that you ought to learn that because they might not necessarily be nice enough to tell you, and this question hasn't been nice enough to tell you that it has a strangeness of +1. You've got to know it. And I also said to you the way that I remember what the K0 is as opposed to the K0 bar is that I find it odd that the real kaon has the anti-strange quark in it. Because kaons are defined by their strangeness, so it's peculiar to me that the real kaon has the anti-strange quark. Don't mind how you remember it. You might remember it that the real one is +1. Whatever you remember. So we know that's true. Now to make plus, we need an up and an anti-down, don't we? Because that's +2/3 and anti-S, sorry, because it's strange. So there you go. There's the quark composition of those two. Now over here, that's the anti of the K plus, isn't it? So that must be a up and a strange. The proton we know is 2 ups and a down. So how do we work out what the strangeness of our omega is? Well, you've got to remember this is strong interaction, and because it's strong interaction, strangeness has got to add up as well. So if we do conservation of strangeness, a strange quark has a strangeness of -1. The proton doesn't have a strangeness. We don't yet know what the omega is. K0, that's anti-strange, so that's +1. K plus, that's an anti-strange, so that's also +1. So what we've got is -1 equals +2. The only way -1 can equal +2 is if we also add in a -3. So the omega minus must have a strangeness of -3 because strangeness must be conserved because it's a strong interaction. I'm not going to attempt to draw the particle interaction diagram for that because it's a strong interaction. It involves gluons. I don't know what those sort of interactions look like. Well, I mean, I know what they look like, but I don't know what this one looks like. So not going there. And of course, not will you. But you could just get a question of that type. It'd be unusual. Okay, so that really does bring us to the end of the particles course. And where I've written what you need to know here, I do mean what you need to know in terms of fundamental particles. I haven't included what you need to know about the photoelectric effect. But in terms of fundamental particles, what do you need to know? You need to know that leptons do not take part in the strong interaction. You need to know that hadrons consist of baryons and mesons and do take part in the strong interaction. You need to know that graph for the strong nuclear interaction. Do you remember that graph? Like that. and you had to mark on 3 femtometers and 0.5 femtometers. If you don't know what I'm talking about, you need to look that graph up. You need to know the conservation rules. Third page of this presentation. You need to know the composition of these particular particles. And you actually can work them all out, providing you know which ones are strange and which ones aren't strange, with exception of the K0 and the K0 bar, where you have to know a little bit extra, as I talked about on the previous page. You need to know the 4 kinds of beta decay. And more than what we did before, not only do you need to know the diagrams and the formulas, but you need to know the diagrams and the formulas either for the complete particle or for the quarks. And you've got to be careful when it's an exam question, because if the exam question suggests it wants it in quarks and you give it in particles, you've probably thrown away half the marks. You need to know how to deduce the properties and the quark composition of particles from the conservation rules. That's what we've just been practicing. That's what those previous 4 examples were all about. Now, these questions are not common. So if you found all of that I was doing on those previous 4 really difficult and you didn't really know what I was up to, then I don't think that's the end of the world. I wouldn't be beating myself up about that. You know, if you don't understand how to calculate the force through a wire at an angle, that's a problem, because a force through a wire at an angle is almost certainly going to turn up in your exam somewhere. This, you know, there's a pretty low possibility of it turning up. I mean, it can still turn up, but even if it does turn up, it may not be big marks. This one, however, I think is quite likely to turn up. Calculations for pair production and annihilation, where you've got to change the rest energy in MEV into frequencies and wavelengths for the photons involved. That's very likely, because it's a nice calculation question, a few stages to the calculation, nice defined answers, and good chances for weaker students to trip up. So a weaker student may well not remember to convert into between EV and joules. Remember, you can't do calculations in EV, you've got to turn it into joules first. So you've got to multiply by 1.6 times 10 to the minus 19. A good student, but not quite as good as they should be, student might forget to include the M bit, forget to include the times 10 to 6 for the million, and so be a million out in their final answer. Nice marks that the examiner can dock there that will distinguish between the A students and the B students. And then, of course, there's the photon frequencies and the photon wavelengths. Which one have they asked you for? Are you using HF because they've asked you for photon frequency, or are you using HC over lambda because they've asked you for photon wavelength? And a weaker student, not going to make that distinction between those two. Somebody's going to get an A or a B, going to realise which one they've been asked for and do it correctly. So these questions appeal to examiners. These questions, less so, because only really the top students are going to be answering those. So if you found this stuff hard, worry about this stuff. Okay, you've got to divide and conquer a little bit. You've got to pick your strengths, pick the things that you think are going to really like to turn up in the exam, and worry about those if you're not finding it all straightforward. Hope you've enjoyed the particles course. I really enjoyed teaching the particles course, so I'm really sad that I didn't do it in person, because I really enjoyed the particles course. But I've actually quite enjoyed researching these PowerPoints, these narrated PowerPoints for you as well. I've found out a few little snippets and things that I didn't know before as I've been going along and putting all this together for you, where I've been double checking it and trying to make it interesting. So I do hope you've enjoyed some of it. I say I have quite enjoyed putting these PowerPoints together for you. I think the Particles course is a really good course, and it's the thing I enjoy about the AQA level, and it's part of the reason why we stick with the AQA level. But of course, we're now on to telescopes in the main course, and so make sure you watch those videos too. Okay, thank you very much.